Hi, welcome back to this class. This class is about the differential evolution, part one. This is Tarik Rashid, and part two will be an implementation of a test function on differential evolution. Now, DE is a population-based optimization algorithm implemented for solving continuous optimization problems or issues. This algorithm considered to be part of the evolution algorithm, AES, alongside genetic algorithm. This comes after genetic algorithm, evolutionary strategies, and particle swarm optimization, PSO. Now, D particularly effective for continuous parameter optimization, nonlinear functions, multimodal problems, engineering optimization, hyperparameter tuning in machine learning. History of differential evolution, or DE, it was coined by Rainer Stone and Kenneth Price in 1995. Their landmark paper, Stone R and Price K in 1997, Differential Evolution, a simple and efficient heuristic for global optimization over continuous spaces. The paper or article was published in Journal of Global Optimization. Now, DE became widely used simply due to its simplicity, its robustness, and easiness to be implemented. And it requires a few control parameters, so it has fewer parameters to work with. Now, algorithm does crossover, mutation, and selection. So that's how the algorithm works. There are a few equations that can be explained, and they'll do it. So this is the algorithm: start, initial population, and then evaluate and population or select through the fitness function, and then use for each target vector do mutation with this equation. Do mutation, and then do crossover, and then go do selection with greedy methods. And we talk about each one of them. And then it goes to evaluate new population. If it is convergence, if the convergence is arrived, then stop or go back and do the same thing. Take for each target vector and do mutation, crossover, selection, and then evaluate the solution. So that is that why DE was developed. Well, genetic algorithm used binary chromosome. Evolutionary strategy relied heavily on mutation adaptation problems. We had in earlier premature convergence, genetic drift, complex encoding. DE solved all this by using real valued vectors. So instead of just binary 0 or 1, it uses real valued vectors directly, dynamic mutation step size, self-adaptive search behavior. This makes DE more stable than many genetic algorithms. Now, basic idea, you've got a candidate of solution, and then each candidate could have a D dimensions of features. And then there is, for example, if there's a minimize or maximize objective function, so we will try to get minimization of this problem or maximization of this problem through the differential evolution algorithm. Now, major operators for D could be mutation, crossover, selection, and the population size we called NP. We could have four, starting from four population at least, and then we work on them. There's also scaling factor. This should be between 0.5 and 1. There's also crossover rate. This again between 0 and 1, for example. So this is more or less about the evolution algorithm. We will give you a practical example right after this class, so that we will have a good understanding of differential evolution. Thank you very much. Stay tuned, and we wait for the practical example.